The traveling Uber driver is a problem from graph theory. In this problem, we want our Uber driver to travel through all the nodes, take all the passengers or take all the packages, and then come back to the root node. The question is, what was the shortest path for him to take? Basically, this is only one problem among many problems we can find for our Uber drivers on graphs. And what is a graph? If you take a look at just a normal blue-collar working class graph, then what do you see? You see a bunch of nodes, you see a bunch of edges. And then, what are the questions that you could ask about this graph? You could ask whether all the nodes are connected. This is one set of questions. You could ask, what is the shortest path from node A to node B? You could ask, do I have negative cycles on this graph? Negative cycles, we mean if we have weights on the edges, then can we create a negative cycle where the weight that we sum is continuously getting more and more negative? This could be good, for example, for arbitrage trading, but this could also be bad. You could find whether we have a strongly connected components. This is in directed graph. You can find whether we have cycles in subgraphs. So we have a lot of set of problems that you could think of yourself. You could find whether we have trees in the graph, whether we can topologically sort and to actually topologically sort the graph, whether the graph is bipartite. There is a whole set of problems that you could think of in a graph simply because it's a bunch of nodes connected to the number of edges. So it's like all the permutations of problems that you could get. The interesting and the good thing about graph is that we have two basic algorithms, the BFS and the DFS, and you build upon them in order to solve the more complex problems. Okay? So let's start with the DFS, because we take the DFS and the BFS and we build upon them and we solve all the other complex problems that we talked about. This is like a building block. In the DFS, what we are doing is that we are taking our Uber driver and we are telling him, hey, you're going to do this kind of a traversal of all the passengers and the packages that you are going to pick up. What you're going to do is go to the first node, then mark it as visited or pick up the passenger in our case. Then look at all the next passengers that are connected to this node, and then recursively take the next one. So hopefully our Uber driver knows what recursion is. So he would recursively go to the next passenger, pick him up, or in graph theory words, mark it as visited, then look at all the passengers connected to this one, recursively pick up the next one, and so forth. And when he backtracks from the recursion, he would need to pick up the next passenger that he didn't pick up. So basically, these algorithms go through all the vertices and all the edges, which is basically just the size of the graphs, and pick up the passengers, or in graph theory words, mark it as visited. And this is it. When you don't have any next passenger to pick up, just move back, or in graph theory words, backtrack. The traveling Uber driver problem is an NP-hard problem. Why is that? Because we could not find a polynomial time solution algorithm, basically an efficient algorithm, to solve this problem. But given a solution, we can tell in a polynomial time whether this solution is correct or not, and so forth. So we take the basic DFS and BFS algorithms, we find the traveling Uber driver solution problem, we find the minimum spanning trees. Basically, this is like the skeleton. The minimum spanning tree of a graph is if you take a graph and you have like redundant edges, what is the minimum spanning tree that you would connect the nodes that you already have connected? And there are also flows. So if you have a bunch of Uber drivers that are taking passengers and you say, okay, what is the max flow that I can feed through them? Let's say I have an infinite number of passengers coming to station number A, and then there are Uber drivers driving them from one point to another. What is the max flow that I can flow through these drivers? The connected components problem can also be solved with DFS. What is the connected components problem? It's a very simple one. Let's say we have a few neighborhoods and we want to tell our, let's say we have 10 Uber drivers, we want to split them in between the neighborhoods. But when we split them, we want to split them in a way that each one takes control of a certain neighborhood. So we want to find what are the connected nodes. Basically, connected component is a bunch of nodes which are connected. And then we have another bunch of nodes which are connected. It's like multiple subgraphs that are not connected one to another. So we want to find all the connected components and we want to give an ID. So driver number 1 takes connected components number 1 or subgraph number 1. Driver number 2 takes connected components number 2. How do you do this? We have the list of all the nodes in an adjacency list and we just apply the DFS algorithm. Because once you apply the DFS algorithm, the basic thing that you get from it is you traverse all the nodes, right? So if you traverse all the nodes, all the connected nodes, and store some kind of counter, let's start this counter with 0, then we give 0 to all the connected components that we have managed to go through. And then when we finish, we increase the counter to 1. And then because we have all the list of nodes, we have all the list of nodes from 1 to n, then we continue to node number 2. But if it already been marked as a connected component number 0, we don't need to mess with it. So we move on to node number 3. Was it already marked as connected component number 0? Yes. Don't mess with it. Go to node number 3. Was it marked as connected component number 0? No. Then mark it as connected component number 1 and apply the DFS. So we apply the DFS and all the nodes that are connected to this node are going to be marked. And in this way we can find and we can attach a label to all the connected components with certain counter. So as you've seen, we can take the DFS basic algorithm, we can apply it to different problems that you could think about. Just as a plain working class Uber driver, you could think about all these problems. What are the connected components? What is the minimum way I should drive in order to pick up all packages and go back to where I was? Topological sort, find the bridges. A bridge is a single edge which connects subgraph that if you remove them, then you get a separate connected components. And we take those BFS and DFS basic structures which build upon how you build up graphs in adjacency list or adjacency matrix, and upon them you can build more complex graphs. So I think this was very interesting and see you next time.